Cassini began studying Titan 25 years later, it also launched a satellite spy probe called Huygens. The probe penetrated the thick hydrocarbon atmosphere. Life might be found on distant planets orbiting other stars. The problem is getting there. But a new super engine with a propulsion system similar to microwave oven technology is preparing to turbocharge deep space travel. Space probes can boldly go where no human has gone before. But for decades, scientists have wrestled with a harsh reality. Space probes can fail. Every one that succeeds is built upon a half-century of failed missions and shattered dreams. The history begins in the 1960s, with NASA's first attempts to reach Earth's nearest neighbors.
Our first Ranger probes were designed to take images of the moon en route to smashing into the moon, and our first 6 Rangers missed the moon entirely. But we learned quickly, and a few months after the Ranger probes, we sent a successful spacecraft to fly past Venus.
In 1962, the American probe Mariner 2 is the first spacecraft to fly past Venus. It reports that our nearest neighbor is no place like home.
We used to think that Venus might be like a twin sister of Earth, with hot, steamy jungles. Well, the space probes taught us that, sorry, Venus isn't like that.
The NASA probe proves that Venus is too hot and its pressure is too great to support any life. But in 1970, the first probe to land on the planet isn't American, but Soviet.
The Venera probes had an inner shell, an inner hull of titanium that was tough. It could withstand, at least for a while, the crushing pressure and the intense heat of the Venus surface.
So the early probes to Venus got destroyed in just half an hour or under an hour. They were able to take data for only a short amount of time before they got crushed.
But the data sent back before Venera's destruction is precise and surprising.
Conditions on the surface of Venus are hellish. The temperature is about 860 degrees Fahrenheit. That's really, really high. I mean, the boiling point of water is 212 degrees, and lead melts at a temperature slightly lower than 860. So you'd have molten lead on the surface of Venus if you had lead there. It's a really bad place to be.
Venus is an extreme training ground for probe scientists. But there is a more distant and difficult goal, one whose extremes are even more destructive than Venus: the outer planets. And getting there requires more than just a big rocket.
One of the biggest problems with space probes is having enough fuel to get where you're going. You do a rocket burn, you burn a lot of fuel, and if you keep doing a bunch of rocket burns, you're going to run out of fuel, and then your probe is dead.
But there is a solution built into the fabric of the cosmos: gravity.
In the early 60s, it was discovered that we can use the gravity of the planets to assist a spacecraft to speed it up, to fling it further out the solar system. That opened up the outer solar system to exploration.
The technique is called gravity assist, a virtual engine that harnesses the immense gravity of planetary bodies to assist a spacecraft on a planned trajectory.
Hitting a baseball is a lot like a gravitational assist. The space probe comes into a planet, it gets caught by the gravity and redirected in another direction, just like hitting a baseball with a bat, and it directs the baseball in another direction.
When the bat collides with the baseball, it changes the baseball's direction of motion, and it can propel that baseball with a much greater speed than what it originally had.
By harnessing the gravitational pull of planets, NASA has been able to hit probes out of the park and to the outer planets. Cassini's home run journey covered 170 million miles to the methane lakes of Saturn's moon, Titan.
Without those gravity assists, this spacecraft, which weighs 12 tons in Earth's gravity, never would have made it to the outer solar system. We don't have a booster big enough to send it to Saturn directly. We would not have explored Saturn were it not for the gravity of the inner planets.
Now, 21st century space exploration is poised to send probes beyond the outer planets, to distant stars. But gravity assist doesn't have the power to get us there. Traveling into deep space requires propulsion that seems to come straight out of science fiction. The ion drive.
Ion engines are like a mini linear accelerator. You accelerate ions out the back, the spacecraft goes.
And you have to transport all that stuff out there. And that means the rockets that launch the spacecraft have to be even more powerful, even more expensive.
Lightweight ion engines have already passed the test in outer space. They power...
Could cut the travel time to Mars down to just a mere few weeks.
5 weeks to Mars is only the beginning. Step in ion drives will amp up its speed as much as destination. One space probe is right now scanning the heavens for that destination. A new Earth and possibly a new form of life. Space probes are on the cutting edge of one of humanity's oldest quests. The search for another Earth. Now, a new generation of robotic explorers seeks evidence of extrasolar planets. And we're finding them.
An extrasolar planet is simply a planet that orbits another star. We have 8 major planets orbiting our sun, and our sun is a typical star. And so a question that has loomed for centuries is whether there are planets that orbit the stars that we see at night.
Since the days of Galileo, scientists have believed there must be other planets among the billions of stars in the sky. But the quest for extrasolar or exoplanets wasn't successful until 400 years after Galileo. In 1995, in the Pegasus constellation, just 50 light-years from Earth, scientists discovered the first true extrasolar planet, 51 Pegasi b. It was found only through indirect clues.
We were only being able to find these extrasolar planets using a technique called star wobble. If you have a big planet like a Jupiter out there, it would cause the star's motion to wobble. But we couldn't really sort of directly tell it was there.
Also called the Doppler effect, the wobble is observed through a telescope. If the star's light regularly shifts toward red or blue wavelengths, and then back again, then an orbiting planet must be causing the light to shift.
In the last decade or so, astronomers have been extremely lucky to find hundreds of planets around other stars. But the planets we've been finding are the large ones, the Jupiters, the Saturns, some Neptunes. We have not been able to find the Earth-like planets, if they're out there.
There are now hundreds of verified extrasolar planets. But are any of these planets close enough for mankind to explore? That's what Annabelle C. from Erie, Pennsylvania wanted to ask the universe when she texted us. How long would it take for a space probe to reach the nearest exoplanet using the best propulsion available today?
Annabelle, that's a really interesting question. And in fact, there's no set answer. Using today's technology, a space probe could reach another star in about 100,000 years. The nearest known exoplanet is about 10.5 light-years away, but there might be a more nearby one. Or we might improve space propulsion technology in the near future. So maybe we could get that down to about 10,000 years in the relatively near future. But something like 50 to 200,000 years is a good answer for right now.
Finding the Earth-like planets means looking deeper into the cosmos at dimmer and more distant stars. A revolutionary method of watching these dim stars could soon pinpoint the first new Earth. It's called the transit technique, and it offers a dead giveaway that an orbiting planet is crossing between the star and our viewpoint from Earth.
So let's imagine this reflector is like the face of a star, and a bug flying in front of that reflector is like the planet. As the bug goes in front of and around this reflector, it will block a little bit of the light from the reflector, just as would happen when a planet crosses in front of a sun-like star.
The amount of dimming is often less than 0.1% of the star's light output. Barely noticeable, but it's more than enough for one far-sighted space probe that's now scouting the cosmos.
We'd love to know if there's another Earth-like planet out there somewhere, and the Kepler mission has a good chance of being able to see it if there is one.
The Kepler space probe is the powerful eye scientists will use to find the Earth-like planets. The proverbial needles in the haystack. The probe's telescope is using a 95-megapixel camera to watch for the transiting planets.
The Kepler mission is using the so-called transit technique to search for new extrasolar planets. With the transit technique, Kepler is watching thousands of stars, waiting for their light to slightly dim when a planet passes in front of the star.
The Milky Way is composed of billions of stars and potentially billions of Earth-like planets. The odds of finding one Earth orbiting one particular star are very low. So Kepler will train its unblinking eye on many thousands of stars at the same time.
Here I have a DVD to represent a planetary system with the star in the center and a planet going around the outside. And of course, most of the time, the planetary system is tilted to our line of sight. And so as the planet goes around, it never crosses in front of the star, blocking the starlight. But if we're lucky, and the orbital plane of the planet is seen edge-on, then the planet crosses in front of the star, blocking some of the starlight and dimming the star. And so you have to be watching tens or even hundreds of thousands of stars to be lucky enough to catch a few planets that happen to cross right in front of the star.
As the world waits, Kepler watches the distant stars moment by moment. But if it does find a new Earth, what can we actually find out about it? What will it look like? Could there be life?
Once Kepler finds Earth-like planets, and I'm fairly sure it will be successful, the next thing will be to try to analyze the light from that planet. What's the chemical composition of this Earth? Does it have an oxygen atmosphere, or is it just carbon dioxide or methane? Does the planet have continents and oceans, water on the surface?
Currently, we don't have the technology to analyze the atmosphere of a distant Earth-like planet. That's about to change. In 2015, the James Webb Space